Okay, so what we want to talk about today, and again, you got to be kind of patient with me because my voice is broken, as it kind of usually is by the end of the week. So what I have here, again, a simple pendulum, but what I want to talk about something called natural resonant frequencies. I don't know if you remember what a frequency is, but what is a frequency? What do we define what are the units of frequency? In hertz or cycles per second, right? So it's number of repetitions per second. Now I want to be really clear. When we talk about natural resonant frequencies, one of the best ways for you to think about that is by thinking about a kid on a swing. A kid on a swing, a child on a swing, or a person on a swing is going to have a natural resonant frequency. It's going to be, there's going to be a natural number of pushes per second or number of seconds per push that you're going to want to give that kid. So for example, here's a pendulum. And I want you to tell me, am I close to the natural resonant frequency of this pendulum? Ready? Okay, 1, 2, 3, go. Okay, so am I anywhere close to the natural resonant frequency? No. So what is the natural resonant frequency of this pendulum? Well, let's try and figure it out. Can you see the natural resonant frequency of the pendulum? Yes, so do you know what I mean? Every time I put energy into the system, it's at the right moment. Does that make sense? So by applying energy at the right time or in the right kind of, with the right period in between when I add the energy, I can get that thing, I can get this object to the oscillation, the motion of the oscillation can be amplified greater and greater and greater every single time. So it's important for you to understand that this doesn't just apply to kids on a swing, right? When you go to push a child on a swing, it's very easy to hit the natural resonant frequency of that child because the child's moving so slowly, right? You push, so they go, and then they come back, and then you push them. They go, and you come back, and then you push them. But it's important for you to understand that everything, essentially, everything that's at least rigidly made has a natural resonant frequency. Now, I want to ask you, are natural resonant frequencies, right? Our natural resonant frequencies, are they good things or bad things for structures? A natural resonant frequency for a structure like a building, is that a good thing or a bad thing? It's a bad thing. But every building, every structure is going to have a natural resonant frequency. Now, what happens if, for some reason, there's something adding energy into a system at the natural resonant frequency? So, for example, let's say there's a building and some event is adding energy at the right times, right? At the natural resonant frequency of that building. What's going to happen to that building? It's going to start to sway, and eventually, if we add enough energy, Brennan, it's going to collapse. So is it important for engineers and people, architects and stuff like that, is it important for them to understand what the natural resonant frequency of the object that they're building, of the building that they're building, is it important for them to know that? Let's take a look at an example of a situation where they did not take into account the natural resonant frequency of that object. Ah, come on. Ah, get out of here. Get out of my face. So this is the Tacoma Narrows Bridge in the United States. This is in the 1950s. Do you know what's adding energy into this system right now? It's wind. The wind is causing vibrations and oscillations in the bridge at its natural resonant frequency. Right, it's grainy footage and it's not amazing because it's not like people had a lot of time to plan for this thing, right? Yeah. Sorry. Chris, I can't hear you at all. The bridge is actually moving like that, 100%. No, the bridge is actually doing this, right? It's actually doing that, yeah. I do not believe that this footage is sped up or slowed down like a ton, maybe 10% or something, because maybe it's hard to preserve archival footage from the 50s or whatever, but yeah, that my understanding is that it's not sped up or slowed down by a considerable amount.
That's terrifying. Yeah, that's why it looks like analog.
Yeah.
Oh yeah, no, that's a noble man.
That's so real.
Anyways.
Oh no. Get the dog?
I think he came back.
Total collapse.
Total collapse. Like so excited.
No.
Is the car okay?
I don't think the car is okay, bro. You can file an insurance claim, but I'm not sure wobbly bridge was.
my bridge started moving in my car. It fell off the bridge.
Imagine trying to like go on a yacht.
Okay. So, is wind the only event that could cause a building or a structure to start to shake at its natural resonant frequency? No. What else could? Yeah, there you go. Earthquakes. So, if you lived in an area that was really seismically active, you know what that means, seismically active? Like tectonic plates, earthquakes, that kind of thing. So if you lived in an area that was really seismically active, then engineers who build buildings in those areas, they would have to take that into account. Does Alberta have to take into account, do we have to consider in our building codes a high likelihood for seismic activity or earthquakes? No, Alberta is not seismically active. To a certain extent, everywhere is like a little bit seismically active, just because you can never really truly predict what's going to happen. But obviously, Alberta is not anywhere close to a fault line, so we don't have to really take that into account. Do you know of any locations on the Earth? Do you know of any places where earthquakes are a thing and they happen a lot and they have to be taken into consideration for the buildings? Rufus? Japan is one place. Absolutely 100%, right? So Japan is essentially that island was created because volcanoes of the subduction of the Pacific plate under the Eurasian plate or whatever. I don't know, something like that. So what they have to do is they have to engineer buildings in order for them to be able to withstand earthquakes. What that means is they have to be able to build structures that can either have a resonant frequency that they don't think is very likely, or they can have a resonant frequency that's like really, really difficult to be able to hit, or the resonant frequency can actually change during certain situations. And so what we can use is we can use something called a tuned mass damper. And essentially what it is, so here's a building, and what it is it's a giant pendulum, and here is the pendulum in the Taipei 101 building or something like that. I don't know, whatever. So there's basically a giant massive object that's being suspended in the middle of the building, and the idea behind it is, here we go. The idea behind it is that if this building starts to shake or wobble, then the tuned mass damper, they call it tuned because it's engineered specifically for this building, and it's a mass dampener because this massive mass can absorb some of the energy of the shaking of the building. Does that make sense? And it can dampen the effects of the earthquake on that building. And so maybe when we come back from the break, we might watch a video about this and whatever, that's totally fine. Anyways, let's write some notes. Yep. This is going to take maybe 5 minutes, and then we're going to do something. Okay, so what a resonant frequency is, when you think of a resonant frequency, it's the frequency that if you added energy into a system that had the ability to oscillate back and forth, is at what rate or at what frequency does that object seem to want to move at? And so what we're talking about here is we're talking about like how can we get the maximum amplitude out of an oscillating object, for better or for worse. So a resonant frequency is the natural frequency that an object oscillates at. Think of a guitar string, right? When you pluck a guitar string, it's going to oscillate at a very specific frequency. If you had the ability to add energy at a matching frequency, you would get the guitar string, instead of just going back and forth, if you were able to add energy at the same frequency, so every time it went this way, you push it that way, and then you let go, and then you push it that way again, and you let go. Then what's going to happen to the amplitude of that guitar string? What's going to happen to the displacement of the guitar string? It's going to increase every single time, right? If you keep adding energy at the resonant frequency, it's going to go from this to this to this to that, and then eventually it's going to snap, or the structure is going to break. So it depends on the physical structure of the object or the building or the whatever the heck you're talking about. So if we were to draw a graph, and if we were to say, okay, amplitude is like, what's the maximum distance we can make this thing oscillate back and forth at, right? So if we were to talk about amplitude, let's say we had an object and we tested a bunch of frequencies. So we're going to add energy at a bunch of different frequencies. What we would see is that some frequencies don't cause a really big amplitude at all. But as you get really close to what we call F0, the natural resonant frequency of that thing, as you get closer and closer to the natural resonant frequency, you can cause really sharp increases in the amplitude of it, right? So if I'm pushing on an object and I'm not nowhere close to that resonant frequency, every time I push on it, sometimes I'm adding energy, sometimes I'm taking away energy. So I'm not really causing a big amplitude change. But as I get close to that natural resonant frequency, then I'm timing the input of energy appropriately, and it's causing a greater oscillation, a greater amplitude every single time, up to a certain maximum. I don't know, does that make sense? Kind of, sort of, Chris? F0, that's the resonant frequency. So as you get close to that resonant frequency, then you can cause large changes to the amplitude of the structure. That's what I drew. F0, meaning 0 essentially. Okay, so if we want to maintain the oscillation, we have to add energy close to the natural frequency or the resonant frequency. But to avoid oscillation, we can design them so that their resonant frequency is not common. To avoid oscillation, we design buildings, structures, objects with uncommon resonant frequencies, resonant, in nature. We can also use something called a tune mass damper, and we'll probably talk about that as a little bit of a review when we come back. Okay, so what I would like to do is we're essentially done chapter 7. Not essentially done, we're done chapter 7. That's all of chapter 7. It took 2 days and then 10 extra minutes or 20 extra minutes of class time. So what's going to happen is, obviously, I'm not going to give you a quiz today because that would be cruel and unusual punishment. I'm also not going to give you a quiz when we come back on Monday because that would also be cruel and unusual punishment. So we have kind of a decision to make, right, essentially. When we look at our semester plan, blah. Woo! Here we go. Okay. Okay, so sorry about not putting anything in, the Brightspace calendar for the last couple days, but whatever, it is what it is. So I was really hoping we'd be able to have our Chapter 7 quiz today, but it just wasn't going to happen. It just wasn't going to happen. So we got to put it somewhere around here. What I would like it to be is I would like it to be on the Wednesday, because I would like to come back on the Monday, do a little bit of Chapter 7 review, give you a day for your brains to unmelt themselves, and then have the quiz. Does that make sense? Okay, so that's when we're gonna have that quiz. But I wanna be really clear, this is gonna be a full week. It's gonna be a very, very, very full week. We have to do lots of stuff the whole time. And then we're gonna have our Chapter 7 and 8 combined exam on the 14th. That's the Tuesday. So when we come back, there's only 9 days of classes, and then boom, Bob's your uncle. Good to go. Okay? So I've got one thing that I would like for us to do today. I want to go out into the lab and I want to do a stations review for the Chapter 7 stuff for just the last like 2 and a bit days. That's what I would like to do. You also have your checklist and review booklets. I thought I had one up here, but I don't. You also have your checklist and review booklets. What I would suggest is that you keep the checklist and review booklet for review on the Monday and Tuesday, so that you're prepared for the Wednesday that we come that quiz. Is that okay? Does that make sense? Okay. Somebody emailed me and somebody asked for a review booklet. Now, I want to be really clear. I didn't print off a ton of them because I didn't know how many people wanted them, but I can easily print off more. So what I have here is what's called the golden ticket. The golden ticket is the thing that you will use to replace a mark in our class this semester. So this is a relatively large document, and it does not have to be handed in until, it says January 22nd, but that's just because it's a PDF of a photocopy of a scan of a photocopy of a PDF, like whatever. So your final exam is on this day. I do not want you to hand it in any later than, you know what, actually it says the 22nd, just through sheer dumb luck, that's the same day that I would have said it. So that is the correct day. So that's the day of your final exam. You cannot hand it in any later than this day. So what you have to do is you have to take this, you have to fill out every question with a couple exceptions. I will tell you when we come back from the break which questions to cross off. I just haven't done that yet. But they're later in the thing, so don't worry about it. So I'm not expecting you to complete this for when we come back on that Monday, right? That would be dumb. It would be foolish for you to do all of that work and then have another 2 whole weeks or 3 whole weeks and then have the final exam. Does that make sense? So do a little bit of work if you want to over the break. That's totally fine. I'm going to give this to you. The golden ticket is due on the 22nd. You are going to get very little class time to work on this because we're going to do Chapter 7-8 exam here, and then these 2 days are going to be filled with review of kinematics and dynamics. I am going to give you very little class time to do this, so you got to plan ahead and work with your own schedule to work on it. Does that make sense? Okay, so here's the deal. Don't panic. This is not like a first come, first serve thing, okay? I am going to put these up here. Don't move yet. I am going to put these up here. But if we run out, you just calmly come up to Mr. Walton and you say, hey, Mr. Walton, you ran out. And then I'm going to say to the whole class, I'm going to say, how many people still want one of these? And you're going to put up your hand for as long as it takes for me to count up to that many people, and then I'm going to print off more. Does that make sense? Okay. So you've got 2 things that you have to do. You have to decide whether or not you want one of these right now, Or if you just want to wait until after Christmas, because I don't want anybody to say, oh, Mr. Walton, you gave me one, but then I lost it, right? I don't want that to happen. So don't take one if you're not going to work on it. Just wait until after Christmas. That's number one. You're going to decide whether or not you want one. Number two, you're going to get your formula sheet. You're going to grab a couple sheets of lined paper. You're going to get into a small group. And you're going to grab your calculator and you're going to go out into Science Park and you're going to work on some stations activities for Chapter 7. Ready, set, go. Yeah. Yeah.